Okay, children, let's start the day with a few new math problems.
Chapter 10, Section 2. We will be talking about series, sequences described by polynomials, and change of index in summations. Series is the sum of the terms of a sequence. When the term of a sequence added from the first to some term n, this sum is called series. To indicate a series, the Greek letter corresponding to the capital S, which is called sigma. In the sigma, the lower index, which is n equals 1, means that the n is the counter, and the number 1 is where the counter starts. On the upper index, 10 is the last term added in the series. An stands for the terms that will be added. The whole process is pronounced as the sum from n equals 1 to 10 of a sub n. The summation symbol above means the following. A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 plus A sub 5 plus A sub 6 plus A sub 7 plus A sub 8 plus A sub 9 plus A sub 10. Now for an example. Expand the following series and find the sum. Looking at the example, the equation shows us n equals 0 in the lower index and 4 in the upper index with 2n. We plug the numbers 0 to 4 and get 2 times 0 plus 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. You add them all together and get 20. Next, we'll be looking at finite series and infinite series. Example A is an infinite sequence. An infinite sequence has an upper index of infinity. The summation will keep going on without stopping. Example B is a finite sequence. A finite sequence has a lower index which has a number. The summation will stop at. Recall that the sigma notation, the sum of I equals 1 to n, means that the terms of sequences from the first term to the nth term are added. Example: the sum of k equals 1 to 4 of parentheses k minus 3 times parentheses k plus 2. Replace k with 1 and you get parentheses negative 2 times parentheses k. Now you keep replacing k until the number 4. Multiply and add the numbers up to get negative. Sigma or summation is a linear operator, which means that the nth term can be decomposed into more than one term, and the sum of the terms is equal to the sum of the nth term. Summation A sub n equals summation B sub n plus C sub n plus D sub n plus E sub n is the same as summation A sub n plus summation B sub n plus summation C sub n plus summation D sub n plus summation E sub n. An example of decomposing is summation A sub n equals summation n cubed plus n minus 1 equals summation n cubed plus summation n minus summation 1. If a constant can be factored out from the nth term of a sequence, then the number can be factored out with the summation. Summation A sub n equals summation A B sub n equals A summation B sub n.
Hi everyone, so next part is my part. I don't know if you can see my picture on screen now. I hope you guys could enjoy our presentation and not get bored on it. This should be the mid part of our presentation. That means you guys still got like half more to go with. I'm pretty nervous actually. I don't know if you can get it from my voice, and I might not sitting there with you guys to listening this. I might just go to restroom or something. Anyway, my part is called sequences described by polynomial function. So if we get a problem and it gives us a sequence of numbers and asks us to find the nth term of it, what are we gonna do? We can find the highest exponents by finding the common difference of the numbers. Then we can set up a polynomial function to solve the problem. Let me set a few equations to explain it to you guys. First, for a linear equation, which is y equals ax plus b, and I plugged in 1, 2, 3 into the equation, and we got a plus b, 2a plus b, and 3 plus b, and we do subtraction on them. Then we find a is actually the common difference. And for a quadratic function, which is y equals ax squared plus bx plus c, then I plugged in 1, 2, 3, 4, 5 to equation, and after 2 times subtraction, I find 2a as my common difference. And for a cubic function, which is y equals ax cubed plus bx squared plus cx plus d, and I plugged in 1, 2, 3, 4 into the equation, and after 3 times subtraction, I find my common difference, which is 6a. And for a quadratic function, which is ax power of 4 plus bx cubed plus cx squared plus dx plus e equals to y. I just plugged in 1, 2, 3, 4, 5 into the equation, and after 4 times subtraction, I find 24a as my common difference. So depends on what I just did, we can find that how many times we do subtraction, it's only determined by the highest exponents of the polynomial function. The others are gonna eliminate itself during the process we're finding the common difference. And the other thing is, the time we do subtraction is exactly the number of the highest exponents. For example, for linear function, it's 1, and for quadratic function, it's twice, and for cubic function, we did it like 3 times. And the last thing is, if we try to compare the common difference we found before, which is a, 2a, 6a, and 24a, it's actually equals to a times 1 factorial, a times 2 factorial, a times 3 factorial, and a times 4 factorial. So we can get another equation which is constant difference is equals to a, which is the leading coefficient, times n factorial. N is representing for the highest exponents. Then next I will solve a problem from our file of chapter 10 to show you how to do this kind of problem. So as you can see here, we got like a sequence of number which is -1, 11, 71, 239, 599, and 1259. And the problem asks us to find the nth term of it. So as you can see, I just do subtraction, and I did it like 4 times. Then it's a quadratic function. Then I can set up my polynomial function, which is y equals ax power of 4 plus bx cubed plus cx squared plus dx plus e. Whoa. And here's another tricky thing. We can find the 0th term of this quadratic function if we try to go from the common difference we find up to the first row, then we can find the 0th term of it. Then actually we can find e. Then e is actually equals to -1. Then I set up like 4 equations. I just plugged in like 1, 2, 3, 4 as x, and I plugged in the number the problem given to us like as the answer. Then we can solve the matrix. I'm not gonna talk about solving matrix. You can do it in whatever the way you want. You can do it in Cramer's rule. You can find it you can find the inverse of it. It should be talked about by the previous group of chapter 9. So what we got here is y is equals to x power 4 minus x squared minus 1, which a is equals to 1 and b and d equals to 0, and c is equals to -1 and e is equals to -1. So this is basically how we can solve a problem by using it this way. And I hope you enjoy it, and if you got anything like confuse you, just feel free to ask me. So welcome to next person who's ever behind me. So thank you.
10.2 Change index of the summation. When we use the summation to calculate, the bottom of the summation always beginning from 1. However, in this section, the bottom of the summation is not equal to 1 anymore. Why we need to change the index? Because the calculation will be easier. If the summation from 2 to 5, its value will be 2 plus 3 plus 4 plus 5. If we change the bottom of a summation equal to 1, then its value will be 1 plus 2 plus 3 plus 4. And the top of the summation will be 4. However, we don't want to change the original value, so all of the value need to go out 1. Then it will be as same as the original one. In this case, the summation is from 1 to 5, and its value will be 1 plus 2 plus 3 plus 4 plus 5. If we change the bottom of the summation become to 4, and it also have 5 number, the value will be 4 plus 5 plus 6 plus 7 plus 8, and we will know the top of the summation will be 8. It is same as the last one. We don't want to change the original value, so we need to let the value go down 3, and it will be as same as the original one. Combine these two cases, we will know when the summation goes down 1, the value need to go up 1. If the summation go up 3, the value need to go down 3. In this case, summation from 1 to 10 to I plus 3. If you want to change the bottom, become to 2, and the number between top and bottom is 10, so the top of the summation is 11. Because summation is go up 1, the I need to go down 1. Therefore, it will be 2i minus 1 plus 3. And we simplify will be summation from 2 to 11 to I plus 1. Let's do some example. Number 1. the summation from 2 to 28 n plus 3. Let the bottom become to 1, and the top will be 27. And we know the summation go down 1 and need to be go up 1. So we will got summation from 1 to 27 n plus 4. And we also know summation n will be equal n times n plus 1 divided by 2. So we can plug in the formula. We will get 27 times 28 divided by 2 plus 4 times 27. The answer will be 486. Next example. The summation from 5 to 16 n squared plus 3n plus 10. Let the bottom become to 1, so the top will be 12. We know that the summation is go down 4 and need to go up 4. And that's expression. We will get summation from 1 to 12 n squared plus 8n plus 16 plus 3n plus 12 plus 10. And we will get the summation from 1 to 12 n squared plus 11n plus 13 8. And we also know the summation I squared will be n times n plus 1 times 2n plus 1 divided by 6. And we can put in the formula. Then we got 12 times 13 times 25 divided by 6 plus 12 times 13 divided by 2 plus 13 8 times 12. And the answer will be 1184.
Hello, welcome to 10.3, which is about series and sum formulas. So today we're going to be talking about arithmetic and geometric series and sum formulas and how we can use them to solve problems that we normally couldn't solve. So to start off, we need the sum formulas. The sum formulas are defined in two different types of series, from arithmetic to geometric. The arithmetic sequence sum formulas are Sn equals n, which is the number of items in the series, divided by 2, times a1, which is the first term, plus an, which is the last term. And for geometric, the sum is defined as Sn equals the first term times 1 minus the common ratio to the power of the number of terms, divided by 1 minus r, which is the common ratio again. So let's start off with a homework problem after that. So we're supposed to find the area represented by the shaded squares, which are shaded in purple. And if you notice, it goes from 1/2. It goes from 1/2 times 1/2 to 1/4 times 1/4 to 1/8 times 1/8 for area. So if we keep on going, you need to find the equation of the sum. So the first area is square 1, the big square, or the big square as in the big shaded square, is 1/2 times 1/2, which equals 1/4. Notice the bottom is 4. We'll come back to that in a bit. S2 square 2 equals 1/4 times 1/4, which equals 1/16, which we can simplify as 1 over 4 to the power of 2. And S3 is 1/8 times 1/8, which equals 1 over 64, which is equal to 4 to the power of 3. And so we can derive from these three to get the general formula of Sn equals 1 over 4 to the power of n. Now we just plug it into the sum formula. So the sum from n equals 1 to infinity of 1 over the power of 4 to the power of n is equal to 1/4 times 1 minus 1/4 to the power of infinity divided by 1 minus 1/4. Notice how I've written this here. Well, the thing is, this 1/4 to the power of infinity will go to 0, like it'll speedily go to 0. So we just call it 0. So we're left with 1/4 over 3/4. These cancel out, and we're left with 1/3. And then for another little homework problem, we're going to find the area of the circles given the radii of the circle. So the first circle has 1, and if you didn't know, the radius of a circle is the distance from its middle to its outside. So this is 1, this is 2/3, this is 4/9, this is 8/27, and yada yada yada. So if we keep going, we just plug it into the area formula, which is, if you don't know the area formula for a circle, it will be pi r squared. So the radius of this one is 1, so 1 squared is 1 times pi is pi. Pi times 2/3, the power of 2 is 4 pi over 9. 4 pi over 9 squared, pi times 4 over 9 squared equals 16 pi over 81. So we can say that since 2/3, 2 to the power of 0 over 3 to the power of 0 equals 1, we can say that the area of the circles is equal to pi times 2 to the power of n minus 1 divided by 3 to the power of n minus 1, all of that squared. We just plug it into the sum formula. We plug this giant massive thing, yes, giant massive thing, and again, this cancels out. So we're left with 5 pi over 9 once we do all the cancellations. Thank you for listening, and I'll see you at the end of the video.
Mathematical induction. To verify the formula such as sum of I to the power of 2 and more, we can use mathematical induction. But how does it work? Let's verify sum of I to the power of 2. First, we have to show that the formula works for the first few terms. Then, we suppose that the formula works for kth term, and then we show that the formula works for k plus 1th term using step 2. For the first step, we plug in 1, 2, and 3, and we see that the formula works for all three numbers, and the answer would be 1, 5, and 14 respectively. Now for step 2, we assume that the formula works for kth term. Therefore, we plug in k, and then we see that the answer would be k times k plus 1 times 2k plus 1 divided by 6. Now for step 3, we have to show that the formula works for k plus 1th term. First, we expand the equation and we see that on the left-hand side we have 1 to the power of 2 plus 2 to the power of 2 plus 3 to the power of 2 until k to the power of 2 plus k plus 1 to the power of 2. Now we have to prove that the left-hand side is equal to the right-hand side, which is k plus 1 times k plus 2 times 2k plus 3 divided by 6. On the left-hand side, from element 1 to k, we already know that it equals to k times k plus 1 times 2k plus 1 divided by 6. Therefore, on the left-hand side, we can write k times k plus 1 times 2k plus 1 divided by 6 plus k plus 1 to the power of 2. And on the right-hand side, we have the answer of the formula, which is k plus 1 times k plus 2 times 2k plus 3 divided by 6. Now if we calculate the sum on the left-hand side, we can prove that the left-hand side and the right-hand side are equal, and therefore the formula is verified.
Okay, so partial fractions. In some cases, it's easier to decompose a rational function to simpler fractions that make up the original function. In order to decompose a fraction, the power of the numerator must be less than the power of the denominator, so that when the fraction is graphed as a function, the horizontal asymptote is at y equals 0. If the power of the numerator is equal to or greater than the power of the denominator, then synthetic division can be performed in order to make the fraction decomposable. When the denominator of a fraction is 0, the value of the function is undefined. When graphed, this is called the vertical asymptote. The numbers that are responsible for vertical asymptotes are called poles. These can be found by factoring the equation in the fraction's denominator. The roots of the factored equations are poles, and they can be used to decompose fractions into simpler ones. Let's look at example 1. So we have x plus 1 over x plus 2 times x plus 1. The denominator of the fraction is already factored, so this is a pretty simple one. You decompose this into two fractions because there are two roots. These are a number a over x plus 2 plus a number b over x plus 1. In order that the values of a and b, we must add the fractions using the common denominator of x plus 2 times x plus 1. The numerator becomes a times x plus 1 plus b times x plus 2. Then we set this numerator equal to the numerator of the original fractions, since both of the numerators are equal. We get x plus 1 equals a times x plus 1 plus b times x plus 2. To find the value of a and b, we can use the poles. In this case, the poles are the roots of the factored denominator, x equals negative 2 and x equals negative 1. We then plug in the roots to eliminate these poles and get the values of a and b. When we plug in x equals negative 2, we get the value of a equals 1. When we plug in x equals negative 1, we get the value of b equals 0. Therefore, the fraction x plus 1 over x plus 2 times x plus 1 can be decomposed to 1 over x plus 2. Let's look at the next example, number 2. We have 2x minus 1 over x squared minus x minus 12. The denominator of this function can be factored to become x plus 3 times x minus 4. We then break down the fraction into two simpler fractions, some number a over x plus 3 plus some number b over x minus 4. We then combine the simpler fractions using the common denominator x plus 3 times x minus 4. We get a times x minus 4 plus b times x plus 3 over x plus 3 times x minus 4. To get to the value of a and b, We set the numerator of the new fraction equal to the numerator of the original and get the equation 2x minus 1 equals a times x minus 4 plus b times x plus 3. We can then use the roots of the factored original denominator x equals 4 and x minus 3 to find the values of a and b. We plug x equals 4 into the numerator equation and get b equals 1 for the value of b. We plug x equals negative 3 into the equation and get a equals 1 for the value of a. The fraction 2x minus 1 over x squared minus x minus 12 decomposes into 1 over x plus 3 plus 1 over x minus 4. In example 3, x squared plus 2x plus 1 over x squared plus 2x minus 3. The power of the numerator is equal to the power of the denominator. We don't decompose the fraction like this, so we use synthetic division and divide the denominator x squared plus 2x plus 1 by the denominator x squared plus 2x minus 3. We divide the numerator x squared plus 2x plus 1 by the denominator x squared plus 2x minus 3. From this, we get a new function, 1 plus 4 over x squared plus 2x minus 3. For now, we can ignore the 1 and continue to decompose the fraction, as we normally would. The denominator x squared plus 2x minus 3 factors to x minus 1 times x plus 3. This is further decomposed into subnumber a over x minus 1 plus subnumber b over x plus 3. In order to get these values of a and b, we can combine our new simpler fractions over the common denominator x minus 1 times x plus 3 to get a times x plus 3 plus b times x plus 1 over x minus 1 times x plus 3. We set the numerator a times x plus 3 plus b times x minus 1 equal to the numerator of the original fraction 4. In order to get the values of a and b, we eliminate the poles. Using the roots x equals negative 3 and x equals 1, we plug in x equals 1 into the numerator equation and get a equals 1 for the value of a, and plug in x equals negative 3 into the numerator equation to get b equals negative 1 for the value of b. Therefore, the original fraction x squared plus 2x plus 1 over x squared plus 2x minus 3 can be decomposed to become a 1 plus 1 over x minus 1 minus 1 over x plus 3. In this next example, example 4, we will be decomposing a fraction that has roots with the multiplicity of 2. The fraction is 4 over x squared times x minus 1. Since the sum of the powers of the denominator equal 3, there will be 3 simpler fractions with 3 unknowns. The fraction decomposes into a over x plus b over x squared plus c over x minus 1. We recombine these simpler fractions over a common denominator, x squared times x minus 1. We get ax times x minus 1 plus b times x minus 1 plus cx squared over x squared times x minus 1. We set the numerator of the new fraction equal to the numerator of the original to get 4 equals ax times x minus 1 plus b times x minus 1 plus cx squared. We then multiply the equation out to get 4 equals ax squared minus ax plus bx minus b plus cx squared. We then factor out the x's, which leaves us with x squared times a plus c plus x times negative a plus b minus b. The x squared, x, and the constant on the left side corresponds with the right side, so that you get a system of equations: a plus c equals 0, negative a plus b equals 0, and negative b equals 4. We solve the system to get b equals negative 4, c equals 4, and a equals negative 4. Therefore, the function of 4 over x squared times x minus 1 decomposes into negative 4 over x minus 4 over x squared plus 4 over x plus 1. Although we didn't use the pole elimination method for the last example, it can still be used to decompose fractions in the case that there are roots with a multiplicity of 2 or more. In example number 5, we have 2x minus 4 over x plus 1 squared times x minus 1. Since the sum of the powers in the denominator equals 3, it will be decomposed into 3 simpler fractions. We get a over x plus 1 plus b over x plus 1 squared plus c over x minus 1. We recombine these fractions over the denominator x plus 1 squared times x minus 1. the fractions become a times x plus 1 times x minus 1 plus b times x minus 1 plus c times x plus 1 squared over x plus 1 squared times x minus 1. We set the numerator of the original equal to the numerator of the new and get the equation 2x minus 4 equals a times x plus 1 times x minus 1 plus b times x minus 1 plus c times x plus 1 squared. We then eliminate the poles with the roots x equals 1 and x equals negative 1. We plug x equals 1 into the equation and get c equals negative 2 for the value of c. We then plug in x equals negative 1 into the equation and get b equals 3 for the value of b. In order to get a, we will plug in an arbitrary number for x and the known values of b and c. For the sake of easy algebra, I will use 0 for x. We then get a equals 3 for the value of a. Therefore, the fraction 2x minus 4 over x plus 1 squared times x minus 1 decomposes to become 3 over x plus 1 plus 3 over x plus 1 squared minus 2 over x minus 1. Now in example 6, we will decompose a partial fraction where the prime factors are quadratics. Up until now, we've been decomposing fractions where the prime factors are linear. The fractions we're decomposing is x squared plus 2x plus 5 over x cubed plus x squared plus x plus 1. We can factor the denominator so that the fraction becomes x squared plus 2x plus 5 over x squared plus 1 times x plus 1. X squared plus 1 cannot be factored any further. It is a quadratic. Therefore, when the fraction is being decomposed, we get ax plus b over x squared plus 1 plus c over x plus 1. We use ax plus b because a over x plus 1 plus b over x plus 1 is too general to get us a correct answer for the values of our unknowns. Going forward, we combine the two new factors to get ax plus b times x plus 1 plus c times x squared plus 1 over the common denominator x squared plus 1 times x plus 1. We then set the numerator of the new fraction equal to the numerator of the original factor in order to get the values of a, b, and c. We get the equation x squared plus 2x plus 5 equals ax plus b times x plus 1 plus c times x squared plus 1. We multiply out the right side of the equation to get ax squared plus ax plus bx plus b plus cx squared plus 1. We then factor out the x's and get the equation x squared plus 2x plus 5 equals x squared times a plus c plus x times a plus b plus 1. Since the two sides of the equation correspond, we can get a system of equations and solve for the values of a, b, and c. We get the system a plus c equals 1, a plus b equals 2, and b plus 1 equals 5. From this, we get b equals 4, a equals negative 2, and c equals 3. Therefore, x squared plus 2x plus 5 over x cubed plus 2x plus x plus 1 decomposes to become negative 2x plus 4 over x squared plus 1 plus 3x plus 1. Partial fractions have many applications, one of which is telescopic expansion. In example number 7, we have the summation of 1 over n squared plus n from 1 to 100. We can solve this by first decomposing 1 over n squared plus n. By factoring the denominator, we get 1 over n times n plus 1. We break this down into a over n plus b over n plus 1. We recombine these fractions over the common denominator n times n plus 1 to get a times n plus 1 plus b times n. By setting the new numerator equal to the original numerator, we get a equals 1 and b equals negative 1. The new equation becomes the summation of 1 over n from 1 to 100 minus the summation of 1 over n plus 1 from 1 to 100. We expand the summation and the summations, and after all the values are cancelled, we are left with 1 minus 1 over 101. Therefore, the summation of 1 over n squared plus n from 1 to 100 equals 100 over 101. Telescopic expansion can also be done with the infinite series summations. In example number 8, we have the summation of 1 over n squared plus 3n plus 2 from 1 to infinity. The denominator can be factored to 1 over n plus 1 times n plus 2. This can be decomposed into a over x plus 1 plus b over x plus 2. We recombine the new fractions over the common denominator x plus 1 times x plus 2 to get the new fraction a times x plus 2 plus b times x plus 1 over x plus 1 times x plus 2. We set the new numerator equal to the numerator of the original fraction, and we get 1 equals a times x plus b times x plus 1. We then multiply through the right side to get 1 equals ax plus 2a plus bx plus b. When we factor out the x's and get 1 equals x times a plus b plus 2a plus b, and since the two sides of the equations correspond, we get a system of equations that gives us the values of a and b. We get a plus b equals 0 and 2a plus b equals 1. For our values of a and b, we get a equals 1 and b equals negative 1. So we get the summation of 1 over n plus 1 from 1 to infinity minus the summation of 1 over n plus 2 from 1 to infinity. We expand the summation. Since the summations go on infinitely, we can assume that the values cancel out infinitely. We are left with 1/2. Therefore, the summation of 1 over n squared plus 3n plus 2 from 1 to infinity equals 1/2.